And I would like to invite the next speaker. So we take the Xiyu Chang. Yeah. So the next paper is presented by Xiyu Chang, and it's on next generation global IoT and how to empower massive connectivity with harmonious multi-network coexistence. And Xiyu Chang is a PhD student in Department of Computing at Hong Kong Polytech, supervised by Xianjin Chia and Yuang Ping Cheng. And his interest is in Internet of Things and low power wide area networks.
Thanks for introducing, and hello everyone. Thanks for taking your time to hear my presentation. My name is Xiyu Zhang, and today I would like to give a talk about our latest work towards next generation global IoT, empowering massive connectivity with harmonious multi-network coexistence. This is joint work with Dr. Qianjin Xia, Ms. Runan Li, and Dr. Yuanqing Zheng. So nowadays, LoRaWAN is widely used to provide wireless connectivity for diverse IoT applications, such as smart agriculture, logistics, metering, and smart cities. And LoRaWAN has many advantages. A single LoRaWAN gateway can cover up to 10 kilometers. It supports ultra-low power operation for many years using just one AA battery. It also has high sensitivity for below noise reception. These features make LoRaWAN well suited for IoT deployments. LoRaWAN also has many advantages compared with some traditional wireless, such as the cellular networks. So in cellular, each device, they typically connect to a single cell tower. They operate on a licensed spectrum and are managed by public carriers. But in LoRaWAN, each sensor can be supported by multiple gateways. It provides services at much lower cost based on the unlicensed ISM bands operation. And LoRaWAN supports the public and private deployments, which provide greater flexibility for users. So with such advantages, LoRaWAN has become the de facto standard for supporting IoT connectivity. And today, there are many operators have built their large-scale LoRaWANs across the globe. So here we can find that there are some commercial providers, such as the Sense network. It have deployed hundreds of thousands of gateways covering regions across the EU, the US, Asia, and Australia. And these LoRaWANs are serving as a global IoT infrastructure and aim to interconnect billions of devices across diverse applications. And to support massive IoT connections, LoRaWAN leverages three key mechanisms. So the first, LoRaWAN can operate over multiple channels, allowing many transmissions to happen simultaneously. And second, it uses the orthogonal parameters. It means that many devices can share the same channel without interfering with each other. And third, LoRaWAN employs an ultra-low duty cycle. This helps to make room for many more devices in the network. But even with such capabilities, there are still some issues observed in practical deployments. We deploy your IoT applications into the Sense network, one of the largest global LoRaWAN operators. And during the operation, we observe a severe capacity limit, like how many devices are transmitting currently. The number of supported users is always less than 16, and this indicates a capacity bottleneck in LoRaWANs. Another issue we observe is under the multi-network coexistence. We decide to deploy another network into a local private server, and each network is configured to have more than 16 concurrent transmissions. And under this condition, a surprising result is that neither network can even reach 16 concurrent users, usually much lower than that. And more interestingly, if we added the number from both networks together, the total number of supported users was limited at 16. This shows that for coexisting networks, they are competing for the limited concurrency. So there has been a lot of studies on LoRaWAN capacity issues, and many of them attribute these issues to packet collision, where there are some packets they concurrently transmit on the same channel and use the same data rate, and then none of them will be received. So to address this problem, there are various collision recovery or collision avoidance approaches. For example, for the first, the acquire leverages the hardware imperfection to separate the colliding signals. And the F-track and CSC, they resolve the collisions in a time domain, while the PQ separates the signals in the spatial domain. And on the avoidance side, the LMAC introduces a CSMA-based protocol to reduce collisions. And meanwhile, the XGate proposes a new gateway design to support the more users, and the recent work, HydroNet, they proposes a new paradigm for interference management. And these strategies greatly handle the collision problem. But a drawback of all of them is that they typically require some hardware or software changes to the cause devices, limiting their effectiveness in practice. And a more important question is that, is this packet collision really the major cause of the capacity issues? So to challenge this traditional belief, we conduct an empirical study on LoRaWAN capacity. So here we deploy 20 end nodes that transmit concurrently to a cause gateway. And each of these nodes is configured carefully to ensure there is no ending packet collision or interference. And the red figure shows the packet reception ratio of each node. We can see that even under these collision-free settings, the gateway can only support up to 16 concurrent transmissions. So this raises an important question, is that why is this capacity still limited even without ending collisions? So to understand this limit, we take a closer look at the architecture of the cause gateway. As shown in this figure, a gateway mainly consists of two parts, the packet detector and the packet decoder. Well, the gateway can detect many concurrent transmissions, but only the 16 hardware coders are available. So once more than 16 packets arrive, the extra ones are still be dropped because there's no decoder available. And we can find that this resource limitation, or with the number of decoders, they fundamentally constrain the single gateway's capacity. So here, for the single gateway that has limited capability, then can multiple gateway help improve the capacity? So here we set up another experiment with 3 cause gateways. So in total, they have like 48 decoders. And the capacity performance is shown in the right figure. We can see that adding more gateways does not improve capacity. It just be limited at 16 users. And after our detailed investigation about this, our findings that for all these 3 gateways, they receive the same 16 packets for 3 copies, and they all drop the same other packets. And if you look at the left part of this figure, it displays the packet arriving time to these gateways. The arriving order is the same for all 3 of them. And since these gateways follows a first-come, first-served decoding policy, then all of them will decode the same early packets and discard the same late ones. So no matter how many gateways we add, but they all will just receive the same first arrived 16 packets for multiple copies, and none of them will receive later ones. And we call this inefficient behavior as homogeneous reception. And next, let's take a look at another issue across coexistence networks. So in this experiment, we deploy 2 networks, each with 10 nodes and its own gateway, and they have different network IDs. So here, ideally, each network can support its own nodes. But if you look at these results on the right side, the later arriving nodes, such as number 17 to 20, they are failed to be received. And this shows that the 16 user capacity is not per network capacity, but shared across all the coexisting ones. So in other words, all nodes compete for the decoder resources at every gateways. So why would this happen? If we look at these figures, they plot the gateway architecture, and for next, they plot the frame structure of a LoRaWAN packet. The network identifier are embedded in the payload. So if a gateway wants to know the network ID for some like the packet filtering, then for any incoming packets, it requires the packet decoder to process the payload and then extract identifier information. So as a result, so all these incoming packets, regardless of their network IDs, will contend for the capacity, or we say the 16 decoders. So from all these explorations, we can find that excluding the packet collision, there are many other factors that lead to the LoRaWAN capacity issues. So from the single gateway's capability, the inefficiency with multiple gateway reception to the resource contentions across coexisting networks. And these are very different from some traditional believed cause like collisions and interference. And our finding is that even packets can be successfully received without collisions, but many of them are still dropped because the severe contentions for decoders from intra and inter-network users. And we call this newly identified cause as the decoder contention problem. So we further examine the practical impact of the decoder contention, and these figures display the packet loss ratios introduced by different factors. So from the left figure, we observe that the decoder contention becomes increasingly critical as the network scales. And more importantly, even with some small-scale deployments, as shown in the right figure, but the decoder contention between the coexisting networks is still highly degrades the reception performance across all these networks. So to mitigate this decoder contention, we accordingly propose 4 design principles based on these factors. For single gateway's capability, we can equip each gateway with more decoders, increase its total capacity, and reduce the contentions. And for multiple gateways, our idea is to configure gateways with more diverse channel settings to avoid homogeneous reception and logically distribute users across gateways that reduce some unnecessary contentions. And for coexisting networks, we aim to isolate these networks with misaligned frequencies, so traffic from one network does not affect the reception in another. And based on these 4 principles, we propose 8 strategies to mitigate the decoder contention problem, but not all of them work well in practical deployments. So here we select 4 strategies for implementation, and these strategies are supported by COTS devices remaining compatible with legacy systems and comply with the ISM regulations. And there are 2 parts for the implementation. First part, we formulate a channel planning problem about how to find the optimal channel configurations for all the gateways and end devices. It minimizes the packet loss risk for all the users. And for second part, we wisely assign different operators with channel plans that are misaligned in frequency. And more details can be found in our paper. And this figure shows the architecture of our Alpha-1 system. The intra-network channel planning is handled within each operator's network server, while the inter-network coordination is delegated to a centralized cloud server. An operator can register with the Alpha-1 system to obtain the customized channel plan for capacity grid. And we evaluate our Alpha-1 system in real-world deployment. We implement the strategies in an open-source network server and compare Alpha-1 with some state-of-the-arts. We first take a look at the capacity of a single LoRaWAN network. So here we increase the number of deployed gateways and recorded the maximum number of received users. We can find that for standard LoRaWAN, regardless of how many gateways we add, the capacity is just highly limited. But in the Alpha-1, the capacity scales linearly with the increasing number of gateways and eventually reaches the theoretical maximum. We also look at how Alpha-1 performs when multiple networks coexist. We gradually increase the number of coexisting networks and measure per network capacity and per megahertz capacity. From the white line, we can see that the standard LoRaWAN, they quickly drops in the capacity, but the Alpha-1 maintains a high capacity. And it achieves nearly 8 times higher capacity than standard LoRaWAN. And we also compared our scalability performance with state-of-the-art solutions. We can see that with the network scales, Alpha-1 delivers scalable performance and outperformed by state-of-the-art strategies. So in summary, in this work, we demonstrate that the operational LoRaWANs fall short of capacity due to a newly identified decoder contention problem. And we explore the strategies to address this problem and investigate their feasibility for real-world operations. And then we finally present the Alpha-1 system to comprehensively manage the intra-network and the inter-network contentions. Thanks for listening, and I would be happy to take any questions.
Thank you very much for the very nice presentation. We have again time for questions. Anna?
Thank you for the nice presentation. And I'm going to ask a question. Maybe I didn't get this right, but one of the reasons that LoRaWAN doesn't use different frequencies usually is that you don't need to do the attachment procedures. And here you would need, so how would each device know which frequency to use and which to attach to?
Sorry, can you repeat this question? So I think for here the voice is...
So first, I understood, you identified this problem of decoder contention.
Yeah.
Right? So you propose to address it by using different frequencies, as I understood?
Let me return to this part. Yeah. So
right. Using multiple channels.
Yeah. There are different principles to solve this problem from different directions. Yeah. So here, let me explain again. Okay. So for the first principles in here, like we want to like improve the capability of a gateway.
Yes, but it would mean that you would need to have a procedure which is currently not part of the system, to attach the devices to different networks.
You mean we can add more gateways, or sorry, more decoders for this, or?
Okay. I don't know how to explain.
Okay, maybe we discuss this in the coffee break. Are there more questions?
Just the question is about how to assign different sequences to different devices and then make the devices to dynamically in the procedure to attach to different channels. That is the frequencies, that is to make it possible to arrange the load in arrange level in different devices to separate the channels and the frequencies to all the devices to make the multiple gateways to be availably used or accessed by the devices. That is a question I think, yeah.
Yeah, let me see. For this decoder contention problem, we can use like for frequency planning to solve this, because if we can see, look at so for this figure, we can configure different gateways or different and devices with different frequency or with different channels. And then for these gateways, they will not receive the same for all the packets. It's not the same arriving orders. Then maybe for different gateways, they can receive different sets of packets. And then maybe we can achieve a higher capacity with the same numbers of gateways in here. And for the end devices, we can configure their frequencies. Like for different end devices, we just set a part of the channels for them to choose the different gateways, and then they will like logically distribute different users to different gateways, and then for the overall capacity, it will be enhanced.
Okay, thank you. So that's just a continued question about it. So should be a policy in each device that it shares the same policies to make it possible to availably or in average level to select the right frequency and not to contention into the same frequency. I think there should be a policy applied in all the devices to do that.
For the LoRaWAN standard, they can they follow the same frequency for all these devices, for the gateways and for the end nodes. But in the for the private deployments, like for example, they can set different gateways and different end nodes in different frequencies, and this can be achieved in the host devices for the gateways and end nodes. Yeah.
Okay, thank you.
I think also I have a similar question to the same talk before, because this requires the coordination between the different operators, right?
Yeah.
So the first question is, again, how do we incentivize the different operators to coordinate, and maybe with, I don't know, pricing scheme or whatever, and in order to come to your full deployment that you foresee, and what will happen if only part of the operator cooperate and some operator not?
Yeah. This is a very good question. And actually, we evaluated the performance well. Some operators, they joined this L1 system, and some did not. For that performance, you can see the details in your paper. And for that part, if for all the operators they join the L1 system, then all of them will have a higher performance than before. But for partial operators, if they join this network, this L1 system, they can still get some higher capacity, but not that higher than if all the operators they join the networks. Yeah, you can find details about this part in our paper.
Okay, let's thank the speaker again, and I think the other question we can do in the coffee break. Thank you.
Okay.